Okay, so now it's time to have some fun with derivatives and integrals. So if you have a vector valued function like this, basically you get 3 for the price of 1. Because what you need to do is, to take the derivative of this function, just go ahead and take the derivative of each component separately. So for this first example, the derivative is going to be, the derivative of 1 over t is negative 1 over t squared. Of course, if you don't remember that one that way, you could rewrite this as t to the negative 1 and then do the power rule and then simplify it and you'll get this. What's the derivative of 2t, you might think? Well, that's 2. And the derivative of tangent is secant squared. Now it could be that the function is written with the ijk notation. So this one's going to be 2I minus 3t squared for the j component and plus e to the 12t for the k component. Then what's the derivative? Well, this is just the number 2, so its derivative is 0. And you could literally write 0 times I, but 0 times it's just going to be 0, so that's actually gone. For this one, it would be negative 6t for the j component. The derivative of the e function is just the e function, but then the chain rule means you need to multiply by 12. So this one will be 12 e to the 12t for the k component. Okay, let's just do one more derivative. How about if r of t is equal to sine inverse of t squared? The next component is the natural log of the square root of t, and then a 4. So the derivative is going to be, so the derivative for sine inverse is 1 divided by the square root of 1 minus, and then the argument needs to be squared. So t squared needs to be squared, which makes it t to the 4th. And then don't forget the chain rule. The derivative of the inside part right here is going to be a 2t. So times 2t. The derivative of the natural log function is 1 divided by whatever is in the argument. And then we need to do the chain rule. Take the derivative of the square root. The derivative of the square root function is 1 over 2 times the square root. If you don't remember that one that way, then you can right here rewrite this as t to the 1/2 and then do the power rule and then simplify and you'll get this. And the derivative of 4 is 0. So this one needs to be cleaned up just a little bit right here. So the first part is just 2t over the square root of 1 minus t to the 4th. In here, the radical t times the radical t, that's just going to be t, so it's 1 over 2t, and then 0. All right, so those are derivatives. How about integrals? So if you have the integral of a vector valued function, let's go with t cubed and sine of t and the square root of t. And we're integrating with respect to t. So this is going to be for the first component. Add 1 to the exponent and divide by that number, so it's t to the 4th over 4. What about the constant of integration, you're saying? That is a good question, but I'm just going to save that for the end. So the antiderivative for sine is actually negative cosine of t. And then for this one, you could rewrite it as t to the 1/2. And when you integrate, it becomes t to the 3/2 divided by 3/2. Or in other words, it's 2/3 t to the 3/2. And then plus the constant. And the constant would be a vector. So you can either have it this way, where the constant is the vector c1, comma, c2, comma, c3, or you could attach each of the constants to each of the components. So this one would be t to the 4 over 4 plus constant 1, negative cosine of t plus constant 2, and then 2/3 t to the 3/2 plus constant 3. And there's the antiderivative. So it would be fun to do integrals like this all day long, but they do show up in other ways, like with differential equations. So it could be that it says the derivative is equal to negative t squared plus 1 over t plus 1. So that's the derivative. And the initial condition is that r of 0 is the vector negative 1/2, 1/3, 0. So what was the original function r? Well, since that's the derivative, we need to do the antiderivative. So that means that r is equal to, so the antiderivative of this one would be negative t squared over 2. And you can either put the constants at the end as a vector, or you can just add them in individually in here, whichever method you like. This one will be t cubed over 3, and then plus its own constant. And then this one is just like having 1 over t, so the antiderivative is going to be the natural log. So it'll be the natural log of t plus 1, and then plus its own constant. And then this is saying, if you plug in a 0, you should get a negative 1/2 here, 1/3, and a 0. So let's see. If you plug in 0, that means that this one is going to be 0, and then c1. This one would be 0, and c2. And then this would be the natural log. When you plug in a 0 right here, it's going to be the natural log of 1. And the natural log of 1 is 0, so that just leaves c3. And then this was saying you should have gotten a negative 1/2, so that's c1, a 1/3, so that's c2, and 0 for c3. So therefore, my final answer is r of t is equal to negative t squared over 2 for that part, and then c1 must equal a negative 1/2. And for the middle part, it's going to be t cubed over 3, and then c2 has to equal this 1/3. And for the last one, it will be the natural log of t plus 1, and then c3 is 0. So that one is finished. But wait, there's more. How about if we get another differential equation, but this time it says the second derivative is equal to negative 5k. Also, r of 0 is equal to 20k. Also, the derivative, when you evaluate that at t equals 0, you're going to get an I plus a j. So there is all of the original information. Because this is the second derivative, we're going to have to do antiderivative twice. So one time will look like this. The antiderivative will equal. Now, this vector right here is the same thing as saying 0, 0, negative 5. So what was sitting right here, so that when I take its derivative, it's a 0. This must have been a constant. And for the second component, it also must have been a constant. For the last component, this must be of negative 5t plus a third constant. Now this part is saying if you have the derivative and you plug in a 0, you're going to get 1, 1, 0. So if I plug in 0 for t, C1 will just sit there, C2 will sit there patiently, and then plug in a 0 right here so that part's gone, and then it leaves C3. And this part is saying that I should have gotten 1, 1, 0. 1 for I, 1 for j, 0 for k. So that means this is a 1, 1, 0. So put a 1, 1, 0. So r prime is equal to 1, 1, and then negative 5t plus 0. Okay, now we have the first derivative. Now integrate that. So r of t is equal to, the antiderivative of 1 is t, the antiderivative of 1 is t, and the antiderivative here will be negative 5t squared over 2. And then you could put plus a constant vector at the end. And I already used C1, C2, C3, so I really, if I want to replace this, I should call it like C4, C5, C6. Anyway, the last part is, if you plug in a 0, you're just going to get a 20 right here. So if I plug in a 0, then I would get 0, 0, and 0, plus the constant vector. And this is saying that the last component should be a 20. So this means this is 0, 0, and 20. So as far as the constant goes, that's the constant vector. So finally, my answer is, this would be t, and then the constant 0. This one is also t and the constant 0. And then this one is negative 5t squared over 2 and the constant 20. And that is the final answer for that one. Okay, so now if you need to take a little break and get a cup of coffee or something, you might want to do that, because this next one is going to take a little while. And this is an application. And basically in this section, all the applications are based on this idea. So this is going to be the ground. And then suppose that you happen to have a cannon, and you point your cannon like this at an angle of theta. And then you're going to fire a projectile, aka a cannonball, and it's going to go out, and then eventually gravity is going to pull it back down. So it's going to go flying through the air like this. So right here is going to be the initial velocity. So as the cannonball leaves the end of the cannon right here, then how fast was it going? That is v0. Now from the end of the cannon goes straight down to the ground, and we would have horizontal components and vertical components, x and y. So you can just use sine and cosine. So cosine of theta is equal to adjacent over hypotenuse And then if I do sine of theta is opposite over hypotenuse. And in here I could solve for x, so it's going to be the initial velocity times cosine of theta. So as this cannonball leaves the end of the cannon right here, it's going both up and to the right. And then this part is basically telling you, just as it leaves, how far is it going to the right and how far is it going up. All right, now let's say that this, so you basically have two choices. You could use the metric system if you live somewhere else in the world, or you could use feet and seconds. So let's say that this is in feet per second if you live in the United States or Burma. Then what is the vector valued function that's going to give you this graph right here? So it's going to go like this. So it's a vector valued function. And with this, right now, we just have x and y. So we're assuming that the cannonball is not going to like tumble through the air like this. If it's going like this, that's basically just a parabola. Of course, when you get into physics, you got to consider wind and stuff like that. But for right now, it's just an ideal situation for this cannonball. So if we were talking about feet per second, if this is in feet per second, so this picture right now is in feet per second, you're going to have to multiply this by time. So if you multiply by t seconds, then the seconds will cancel and you'll have something that's in feet. So this part needs to be multiplied by t. Oops, cosine of theta. Started to write the t too soon. Times t. So that's going to be in feet. Now, as far as the height, you can also take this and multiply by t. But the thing is, if you only did that, this thing would go flying up forever. But of course, there's going to be gravity that brings it back down. So then we have to do minus 1/2 whatever you use for the force of gravity times t squared. Now, since we're talking about feet in seconds, then in this case, the force or the acceleration due to gravity is 32 feet per second squared, or per second per second. So that's going to be the function that we use. Now, an example. A projectile is fired at, then I looked at the homework and they used metric system, meters per second at an angle of 50 degrees. That's it. That's the beginning of the question. That's all the information you need. You need to know what angle and what is the initial velocity. Then you can come up with a whole bunch of things. So since this is in the metric system, we're going to have to use that acceleration due to gravity is 9.8 meters per second squared. All right. Use my little formula right here. So the function, so you put the initial velocity, that's 600, and then cosine of 50 degrees times t. And then this part will be the initial velocity of 600 meters per second. I don't need to write that. Meters per second. And then sine of theta, so sine of 50 degrees, t minus 1/2, and then use 9.8 t squared. Okay, so this is going to be our function. And then there's quite a few things that could be asked. Part A. How long until it, that being the particle, is 20 kilometers downrange? So in other words, this is a big gun. This is not like a little BB gun or even a little cannon that they might have at the Civil War. this is like a big gun because they're talking about 20 kilometers downrange. Okay, anyway. Now, one thing is, this is in meters and this is in kilometers. So the first thing you need to do is change this to 20,000 meters. So downrange means basically if it was fired from here, then over here is 20 kilometers. So it's still going to be in the air. It hasn't landed yet. But how long is it going to take until it gets there? Well, that's just talking about this X information right here. So we just need to use this part. So in other words, when does this part equal 20,000 meters? So when does 600 cosine of 50 degrees times t equal 20,000? So all I need to do is divide both sides. So it's going to be 20,000 divided by a 600 and cosine of 50 degrees. So it's in degrees, so that's good. Then 20,000 divided by, put parentheses, 600 cosine of 50 degrees. So 51.857, and that's going to be in seconds. All right, then on to part B. Part B is going to be, when is it at the maximum height? So when is it going to go up, reach the maximum height, and then gravity is going to pull it back down? So when does that happen? Well, since this is the height, then we just need to be using this y value part. What's the maximum y value? So part B, when does it reach maximum height? So we not only need to use this, but then find the maximum of it. So that means take the derivative and set it equal to 0. So take the derivative of this. Well, the derivative of t is 1, so that's just going to be 1 times the 600 sine of 50 degrees minus, take the derivative here, the 2 goes down in front and multiplies, and it's actually going to cancel that 2. So it's going to leave minus 9.8 times t, take the derivative and set it equal to 0. So then I could add the 9.8t to both sides, and then divide both sides by 9.8. So a 600 sine of 50 degrees gets divided by 9.8. So it's going to be 46.901 seconds. Then, part C, what is the max height? And I'm modeling this problem after, I think it's like the last 2 or 3 questions in the homework that are just like this. So part C, find the max height. So we just found out when it's going to reach the maximum height. Since height is just about the y value, all we need to do is plug that in here. So that's going to be 600 sine of 50 degrees, and then plug in the 46.901 seconds, minus 1/2 9.8, and then t gets squared, 46.901 squared. And that's going to be the max height. Now, I could just type this in the calculator, but since I have this right here, I'm just going to go like this. Put store, and then store it as x, or t. Right now it's a t, that's fine. That way, anytime I use that key, it's now going to use 46.901. All right, so we've got 600 sine of 50, and then put t. And minus 1/2 times 9.8, and then t needs to be squared. And it's going to reach 10,778.402 meters. So it's going to be more than 10 kilometers in the air. Like I said, I made this up very close to the homework question, so that's what they're saying, that somebody's going to fire this projectile 10 kilometers into the air. Then part D. Find the total flight time. So if we go back to the original picture, so it's going to take off. So the length of the cannon is not considered in this. So we're just basically saying it's like firing it from here. Anyway, that's a small detail. So it goes, and then it lands safely right here. So how long does it take to get to that point? Well, at this point right here, the y value is 0. So all I need to do is take the y value. In other words, this one right here again, take this one and set it equal to 0, and then solve for t. So in other words, put the y value equal to 0. That is 600 sine of 50 degrees t minus 1/2 9.8 t squared. Oops, I forgot the t. T squared equals 0. Well, since I don't like that squared right there, it's supposed to be right there. Since this has t and this has t, you could factor out t. That's sort of funny because at the beginning I said if you need to go get a cup of coffee, and now I just keep talking about tea. And let's see, what's half of 9.8? That's 4.9. And I'm only factoring out one t, so it still leaves a t right here, 4.9. So this one would be t equals 0. So that's the beginning of the story before it takes off. Then this is going to be the end of the story. So to solve this, you could add that to the other side. It'll become a positive 4.9 t is equal to this 600 sine of 50 degrees. And then just divide both sides by 4.9. So a 600 sine of 50 gets divided by 4.9. So it's going to take more than a minute and a half. It's going to take 93.801 seconds. And for the last question, part W. Oh no, part E. Find the range. So what that means is, fire the projectile, it's going to land downrange. Well, this was 20 kilometers. Where's it going to land? In other words, what's the x value down here? So that means we just use this part, and for t, we plug in that 93.801 that we just found. So the x part is equal to, well, x is equal to initial velocity, which I've got so many papers. What was it? 600. 600 was the initial velocity, and then times cosine of the angle. And then substitute the t that we just got, 93.801. 600 cosine of 50, and then times the 93.801. So this thing is going to land 36,176.472 meters away. That's 36 kilometers away. That's pretty far. All right, that's it. We finally finished all the parts.